Hello everyone and welcome to this video in which I will record my presentation for the Australasian Skill Acquisition Conference of November 2021. And this presentation was about an eye in a head on a body, about a project that we've completed at the University of Innsbruck in collaboration with a master's student, Andy Schmidt. So let's jump straight into this. So in this study, we're talking about visual exploration, and visual exploration really is, as I would argue, the basis of how we interact with the world around us. So if we have this scene, then it affords us certain things. So we use visual exploration to see a chair as sit-onable, a cup as graspable, and some nice cakes as edible. So we build this connection with the world around us using our visual system and using visual information. So this is really at the foundation of how we interact with the world. So in its core, visual exploration really is that interaction with the world around us that establishes the relationship between the person and the environment. And this, of course, has been studied, for instance, in quite recently in football, where results show that the more a player looks around, the more a player moves their head around, the more accurate they will be in their passing, the more their performance improves. And also outside of sport, in walking, for instance, we see that specific visual search strategies are associated with certain risk factors, for instance, for falling. So we see that this relationship between visual exploration and really success in movement is all around. It's in sport as well as everyday life. And then it's good to know that historically this research on visual exploration has been centered mostly around the eye. So looking at eye tracking outcomes, what is the eye doing and how can we interpret that in terms of movement control. But more recently, there has been a shift in focus towards the eye-head-body system. Not just considering the eye, but considering the entire system in this control. And that's really where we position this study as well. And to do this, we use principal component analysis to analyze visual exploration during gait. So as a quick introduction to principal component analysis, this is an analysis tool that takes a data set, and in that data set we of course have variability, we have variance, and then it starts to group this variance. So it looks for a linear relationship in the data set, so we can get bundles of variance together and then interpret these separately. So what does that look like in movement control? Well, for instance, if we have this walking movement that our assistant here shows, and then this complete movement pattern has variance, which is accumulates to 100%. So let's visualize that with a full circle. And then we can start to divide this whole body movement pattern into principal components of linearly related positions, marker positions or segment positions that usually occur together, which is where that relationship then comes from. So in walking, what we usually see is that there's a really big first component that covers about 80% of the variance already, and that encapsulates then arm and leg swing. So really those forward-backward movements account for most of that variance in the data set. But then there's still more, about 6% or so is usually knee flexion and extension, which we can visualize as well. We have mediolateral weight shifts as a usual third component, and a fourth component could be the vertical whole body movement. But this will depend massively as well on the data set you're using and the specific details of the analysis. What is always the same is that in total, this movement pattern adds up to 100%. So in total, principal component analysis, all of the components together add up to this 100% variance. But what we see is that we can already represent a lot of this movement pattern, so maybe over 90% in the first 2 or 3 components, and that's quite similar for a lot of different movements. So how are we going to use this in our study? The aim of the study is to assess whether exploratory head movements during walking are connected to movement patterns distributed over the whole body. If so, what do we expect to find? Then we can use principal component analysis to detect components that are dominated by head movement alone. So then we find isolated movement components that just cover the head markers and do not really connect to any other distributed marker in the body. So this is what we'll be looking at, and how we assess this is of course with our experimental design. We had a participant on a treadmill walking on the treadmill, and 4 meters in front of the treadmill was a wall on which we positioned LEDs that could either turn on or off, as LEDs do. So to the here represented on the top and the bottom, but to the sides in real life, this would be an optical angle of about 20% for the participant. So we're looking at 20%, 20 degrees. So we're looking at 20 degrees head movements in this situation. Aside from these 3 LEDs on the wall, we also positioned one LED about 2 steps in front of the participant. This is because this 2-step margin has been found in previous literature to be relevant. This is usually the distance as close to our body as we usually focus our gaze in our visual exploration during walking. So another one right there. So how does this look then for the participant? We switched the treadmill on to 4 kilometers an hour, and then we made these LEDs flash in different settings. So first up, a condition with horizontal flashing, and the participants every time had to track the LED that was switched on. So this should afford horizontal head movements. Second condition for vertical head movement, so just the center 2 LEDs were used here. And lastly, we had a randomized condition, a mixed condition with both horizontal and vertical movements in there in a manner that was unpredictable for the participant. So in total, we did this with 21 participants, and we used a 39 marker Viken plug-in gate set to record whole body movement coordination. So what was found, first have a look at these lower order PCA outcomes, and what we see, just like Mario illustrated before, we see a first component that is quite heavily dominated by the legs here. So the arm and the leg swing quite heavily dominated here. We used a weighted PCA, which means that the heavier body parts are represented more. So in this case, we see a little bit more dominance of the leg markers, but we'll illustrate that on the next slide. Second component, also leg movement. So we see this flexion and extension of the knees. Third component is a synchronized flexion and extension of the knees, and the fourth component is also a quite dominated by the legs, a synchronized leg movement component. And this is what then the marker loadings look like. So in this figure, we've visualized how specific markers attached to specific body parts here contribute to these different principal components. And what we can see is that for these first 4, this is heavily dominated by the leg markers. And as I said, this was a weighted PCA and the legs are quite heavy. If we would have done a unweighted PCA, we would, in that first one, for instance, also see the arms, because there was quite a lot of arm swing as well. But in this case, the legs quite nicely light up. So let's have a look for head movements then, and let's have a look at some more principal components. So here we have the first 30 principal components, And what we can see now is different principal components that might incorporate that head movement. So let's have a look here. These 5 represent principal components that have a contribution bigger than 5% of the head markers. Why did we look at 5%? The head is about 5% of the body weight. So anything above that has a relatively high contribution of the head markers. So more striking perhaps then are these 2, which even had a contribution of the head of over 50% of their loading. So let's look a little bit into a little bit of more detail into these principal components that we found, PC19 and PC23. So these had over 50% of contribution by the head markers, and this is what the videos look like for these components. So PM19, PC19 is clearly this sort of yes nodding pitch movement, and for PM23 we have this horizontal gaze shift, so a yaw movement. And what we can see as well already in these videos is that these don't seem to be isolated, especially that yaw movement seems to be associated with quite clear movement of the arm. And this is then if we look at the marker loadings for these 2 components, and these sort of confirm what we see in the videos already. So PC19 has some associations, especially with the legs, and PC23 has some associations with the whole body, and in particular also that arm movement is represented. And to quantify this a little bit more, what we see is that PC19 adds up to about 72% contribution by the head markers, and PC23 adds up to 66% contribution of the head markers. So even if in these principal components that have a very high loading to the head of the head markers, we still see almost 30% contribution by other whole body structures. So what does that mean? Head movements during gait are associated with whole body movement patterns. It's not isolated activity. We see activation of the entire body when we're using our head, when we're exploring with our head during walking. So what does this mean? This means that what we do with our head might affect our body coordination. And this is a relevant finding if we can confirm this in a more practical setting, because imagine, for instance, when an older adult walks the street and they're constantly looking around, constantly distracted by things in their environment, then that might affect their whole body coordination. It might affect where they place their feet. It might affect whether they stumble then, but also it might affect their general ability to maintain balance because they might not have those compensatory whole body movements available. Also the other way around, what we do with our body might affect visual exploration. So if the same older person is walking around with shopping bags, then that might actually influence their ability to look around and to look for tripping hazards in their environment, and therefore this might be a relevant finding there. But also in a sports setting, we often walk around or run around with things in our hands. If we're running with a ball or running with a hockey stick, then that could potentially affect our ability to explore opportunities for action around us. So we need to be aware of this, and potentially this could lead to new training insights. So that is the end of our presentation. Thank you for watching, and I'd just like to acknowledge again, thanks to Andreas Schmid for helping to create this data set. And if you want to collaborate with us, please get in touch. Thank you for watching.